appropriate. What are any questions? Maybe, or you can tell me your background, then I can at least answer some questions or try to guess the questions before I answer.
Hello, sir. This is Kaushik. If I may start the proceeding in some ways. So I think I had a little trouble placing the frame, or kind of trying to frame as to what we are trying to solve here. In that sense, we started off with the linear model, but then I just wanted to understand the background as to why we came to that in the first place, so that we kind of understand why we framed that model in the first place, and then maybe some help around what background material. Because I mean, we did do stats too and all that, but it's been a while, so unfortunately I haven't brushed up enough. So suddenly when Week-3 kind of hit me a little hard, so it will be good for me to understand, what should I go back and work on, so that it will help me understand Week-3 better, and also subsequent weeks.
Okay, so fine. This is something I can answer. I will answer in a certain way. I will try to give a sort of a background of what's going on. Then we'll come back and you can tell me if I've answered your question or not after that. Is that okay? We'll try that?
Sure, sir.
Yeah,
sure.
Yeah. Anybody else? Any question like this?
Sir, I have only one question. There was an assignment question where we have been asked to find the distribution of SSE, SSW, which is coming to be chi-square with respect to some degree of freedom.
Right.
We are not able to simulate. I think there are a couple of other people as well, as far as I know. So if you can just help us, guide us that how we can get that. I'm not asking for the actual answer, but if you can.
Okay. I will give you. I'll give you a background of sum of squares within, and I'll do something. I'll give you some. Hopefully, it's not repetitive. I'll try to give you some idea of what's going on.
Okay.
I'll try. Very good. Yeah. Okay. Very good. So I have an idea. So what's going on? So Ishan, how much time do I have? Like maybe an.
We can schedule it for 1 hour 13 minutes, but we can extend it if required.
Yeah, no problem. So I will record this on my machine, not your questions, but my sort of whatever I'm speaking on. So after I speak something, I will pause it, so the recording will not be there, and then you can ask questions again, and then we'll proceed in that manner. Okay. So let me start. So I will go two ways. One is I will start with some basic statistics that one needs for this sort of idea. Then I'll come back and then I'll go to this other question that someone asked. Why are we doing all this? Like, what is the framework? Where are we heading towards? That's the next question. Then after that, I'll come and close with I'll give you a sketch of why all these sum of squares become chi-squares. And that's how I'll close. And someone asked me also, why is a linear model? Why linear, why not something else? That I will try to answer in some way. But the answer for why linear is that it's sort of the simplest one can start with. That's why. But anyway, I will try to answer that in some manner as we go along. Okay, very good. This is what I will do. Let me share my screen. Just let me know on chat if you can see my screen. You should see a whiteboard and let's say I'll scribble something. You see a scribble? Can you just tell me on chat if you can see it, and then I can move on. Thank you. Very good. And you can all address me as Siva. You don't have to call me sir. Okay. Thank you. I would prefer that. Okay, very good. Okay, so let me now record a little bit. Let me see if I can. Very good. Let me see if I can record on my computer. And I'll share the recording with Ishan, and he can put it up on the website. That's okay, Ishan. You can put it on the website later on. Ishan is not there. Or?
Yes, sir, we can.
Yeah. Okay. And Ishan, just alert me if my voice goes away or voice doesn't go. Okay.
Yeah.
I'll turn my video off because I think it will help in connectivity. Yeah. Thank you.
Yeah. Thank you.
Okay, very good. So let me start the recording. Okay, so let me begin. See, So this is just I'll start with some basic background in statistics. So basic background in statistics, let's say. So the what I think we should think about is that when we do statistics, we go collect data, and there are some key distributions that we look at, and they're called sampling distributions. So I will just discuss them briefly, and then we'll come back to the question of linear models in a second. So here, so you go to a population and collect, let's say, n data points, x1, x2, xn. These are n points, n samples from a population. Let's call this as random samples from a population. And typically, you're interested in some parameter in the population. That's why you go collect the sample. And this parameter could be many things. Could be sometimes just the mean of the population or certain characteristic population. So that we measure by what? So we have this one important quantity. We say x bar is just 1 over n summation I equal to 1 to n of xi. And this is what we call as the sample mean. Right? Another key characteristic of the sample distribution is called the sample variance. Is denoted by s squared. So s squared is just 1 over n minus 1 summation I equal to 1 to n of xi minus x bar the whole square. This is referred to typically as the sample variance. And one small comment before we go on. This n minus 1 is not so critical, but people like a certain value of the estimator, because this is supposed to estimate the variance of the population. If you normalize it by n, then it will not become what's called an unbiased estimator. That's why people put n minus 1. But you can also put n. It's not really a very, very key aspect of this problem. So now the one of the first theorems one learns in this sort of era of how good these approximations are in terms of the true population is the following idea, following theorem. I'll write the theorem down so that we can all sort of see it a little bit. And this is the fundamental theorem that sort of guides us in evaluating sum of squares as well in across normal random variables and the linear models that we're discussing. So what we do here is that we let x1, x2, xn, x1, x2, xn, these n points, we assume them to be coming from a normal population. So let's say they are all IID, they're all independent and distributed, let's say as normal, with some mean mu and variance sigma squared. Okay, this is something we have. So this is the fundamental assumption about the data. That's where the data is coming from. Then there are three very important conclusions. I'll write the conclusions down. So one is, let's say the first one's A. The conclusion is that this should be straightforward to do, that x bar is just a linear combination of normal random variables. So there's a sort of an interesting property of normal random variables. I don't know why I put equal to there. So x bar is a linear combination, remains normal random variable, and its variance, its mean is just the sum of the variances, sum of the means with the appropriate scaling factor. So it's n of them are there, so when you divide by n, so the mean remains mu. But x bar has a smaller variance, it's sigma squared by n, right? Random variable. So this is sort of a very important result. It tells you that x bar in the long run has smaller and smaller variance, like sigma squared by n. So it will focus on the true mean of the population as n gets larger and larger. That's sort of an important idea in this result to keep in mind. What is it giving? And result number B is that what happens to S squared? So S squared, if you look at S squared, of course, it's not quite clear to you that these are all sort of independent guys in some sense, but these are like squares of normal. So each of them is a square of a normal. So it's chi-squared 1, and there are n of them. But of course, if I know n minus 1 of them and x bar, then I know the nth guy. So I will lose 1 degree of freedom. So that's why it's known that if I have to normalize it, so I'll write it as xn minus 1 by sigma squared times s squared. This follows, this has, so I'll call it as chi-squared n minus 1 degree of distribution. So intuitively, why this is n minus 1 is that I have n data points, right? But in this expression, I'm also assuming I know x bar. So if I know x bar and I know n minus 1 of them, then this guy is for free. That's why this is n minus 1 degree of freedom, intuitively. So these two things are standard to prove. One has to sort of work hard to prove it. But the last one is kind of crucial. It's sort of a nice result, which is why the independent structure comes in a normal population. One immediately is able to also tell you that x bar, sorry, x, I have the blue again, I'm sorry about that. X bar and s squared are independent. So that's sort of the very, very useful result in this area. So the first thing you learn about sampling distributions, and this is a fundamental result to keep in mind. And this is the backbone of everything that you do in terms of sum of squares, sum of treatment squares, error squares, within, or all those things. This is exactly the thing. Of course, now once you have this sort of an immediate corollary, which is also very useful, we do again, is that this is an important corollary. Let me write a corollary down. The corollary is in the same setup as the theorem. So you look at a normal data set, x1 is to normal. Then let me just copy it down so the notation is consistent. So copy it down, put it here. And let me make it a little smaller, so I can write one line. Yeah, and the idea is that you have root n x bar minus mu by s. So if you look at this, the top guy is following normal with mean 0 and variance 1. Variance, if you look at this, how to do this, I'll write it in a little bit clever way so that you can sort of just check it immediately. If you look at this guy is going to give you, at the top, I have root n x bar minus mu. I'll divide by sigma over I'll just keep it as sigma, divide by sigma. And the bottom guy, I'll just remove the n root n here. Right? And I'll divide by the whole thing by, I'll just call this as 1 over n minus 1. And since I've already had a sigma at the top, I have an extra sigma free. I have an n minus 1 at the bottom as well. So I have to multiply that. So I have an n minus 1 by s squared by sigma squared. Okay, that's just an algebra. But then the top guy is normal 0, 1. The bottom guy we know is chi-squared. So this we know is t. This we know is tn minus 1. So this is the backbone of statistics that you must have before we start linear modeling in some sense.
Shiva, can you please scroll up?
Yeah, go ahead. Sorry, go ahead.
Can you please scroll up? I think the bottom is getting cut.
Oh, sorry. Off. Yeah, go ahead. So now it's maybe I'll make it flatter like this time. This is a better way of viewing it. Maybe better.
Yeah, thank you.
Maybe I'll just move this side a little bit. Going inside. Very good. So these are the two results. I hope this is clear to everybody that this forms the fundamentals of everything you do with sum of squares. And see, what will happen is always when you do sum of squares, it'll always look like this. And that's what gives you, it'll look like one normal, its corresponding mean, and squares. That's it. It gives you chi-square immediately, right? And then when it comes to t, it's just you're all identified as the ratio of normal by square root of chi-square. That's it. Correct form. Appropriate degrees of freedom. That's it. So this is the essential backbone of this whole approach. Also, like when you do this, we look at two sum of squares are independent, or like SSW and SSB independent. This is the key result you use, that the mean is independent of these guys. So if you look at the two squares, one will be a function of mean, one will be a function like S squared. That's how we get independence. Okay, so
sir, in the corollary part, I am not able to get the right hand side.
This one?
No, right hand side.
This one?
In between.
This one? Right.
Yes.
So this one, I just algebra. Yeah? I just moved this root n down here. I divide by sigma. So I put another sigma squared here. Everything kind of, it's an exact equality. One n minus one here, and this is jugglery. Why the jugglery was? I wanted to make the top as normal 0, 1, and the bottom as chi-squared n minus 1 divided by the degrees of freedom.
Okay.
So that's what I get t. Right? That's a statistic result. Normal by square root of n1 chi-squared is t. Okay, so is this clear to everybody? Can I move on?
Just one, quick question on C. The point C is so intuitively when we say sample mean and sample variance are independent.
Only the normal case. Only the normal case. Not otherwise it's not true.
Okay.
So that's a sort of an artifact of the normal distribution. You see, it has various nicks and knacks because of the way the density is given to you, and the why is intuitively why it's true. I don't know. The idea is that you can actually show in the proof. You actually show x bar, and each of these guys are independent. That's what you'll show in the proof. You do a proper proof. It's called a method of orthogonal transformation, and that's how you'll show it. See, the formal intuition is that if you take the vector x and you transform it by a linear transformation A, the vector AX is normal with mean A times the mean of U, and variance is A transpose the variance times AA, right? And if you know enough linear algebra, you can choose an A cleverly to make that diagonal, formally speaking. And that's how you get the fact that these two are independent. That's one way of doing it. There's another proof by Cruxell that's induction oriented. That's also easy to, I think the easiest thing to do is check it for k equal to 2. That's an easy thing to check. Like n equal to 2, I mean. Take n equal to 2, and then you can check actually. This is what, x1 plus x2 by 2, right? That's what you get for x bar. This will be what? You just expand the whole thing out. You'll get, I think, something about x1 minus x2 and something about x1 plus x2. That's what this guy will be at. Okay. So then all you have to do is check for two normal random variables. This x1 plus x2 and x1 minus x2 have covariance 0. And that's automatic. And for normal, if the covariance is 0, you get independence.
Right.
So this is a very crucial normal property. Otherwise, it's not true. It's not true otherwise. Yeah, otherwise, in general, sample variance and mean are not independent. Only in the normal case they will be. Okay, that's a good point. Right. Otherwise, it's an important point that we use all the time again and again. Okay. Anything else? Can I move on? Everybody else in chat can let me know. Just following. More questions? Okay. So now this is the first part that someone asked me. Where do we start from? This is where you start from. Okay, so the next thing you want to know. Let me just do a sort of a. I mean, I don't think this is an accurate representation of why we're doing all these things. I'll give you two examples and what's the general framework of where all this started. And you will do this in the course. The course will come along. I didn't design it this way purposefully, but you will learn this all. What I'm going to say, it's a precursor of what's going to come. But I'll give you the context. Maybe I should have done it before, but I did not. Let me record again. So I'll give you a preview of what's called one-way ANOVA. Just a preview. So let me write this down. So let me keep it like this so you can all see the entire board properly, perhaps. So, sorry. So let's say a preview of what people call it as one-way analysis of variance analysis. We will discuss this in the course as the course goes along, but I just wanted to give you a preview so that you have the context. Because I apologize, I don't think I gave an example in the structure of the first few lectures. So let me give you a simple idea. So this is a technique by to determine whether or not population means of multiple samples across them are the same. So let me write down. So let me write this down in sort of in words. So this is a technique by which one can determine if or maybe whether or not population means of multiple samples are the same. The multiple samples are the same. Okay, so what do I mean by this? Let me just I'll just go ahead, give you an example. So let's do an example so that way it's clear to us what we mean by population means across multiple samples. So let's say you're let's do a simple one. You're a biologist or a botanist, let's say maybe a botanist, and you want to observe the effect of soil salinity, like how much salt there is in the soil. So let's say as a botanist, so let me write it on black. So again, as a botanist, let's say you want to observe or you want to understand, you want to determine, let's say you want to determine, to understand, or since I used the word determine before, determine how, let's say soil, maybe soil minerals or soil salinity affects plant growth. So the idea is that you plant in a certain soil and you observe the growth there. So what you do is to do this is the question that you have in mind. That's where you start off from. So to do this, you do the following. What do? So they go and conduct an experiment. They conduct an experiment. And what they do is they take the same species of plant and they place them in different concentrations of salt, okay, of the soil. So they can experiment by growing the same species of plant in, let's say, 3 different concentrations of salt. 3 different concentrations of salt. And measure the plant's height, let's say, and measure the plant height. So the key is the same species, and they do 3 different concentrations, right? To just to assess their hypothesis that, hey, do have a different thing. Measure the plant's height. Height of a plant, let's say in a month's time. Very nice. This is what yeah. So let's say the results. Let's go and tabulate the results. So the results are, let's say the first one was let's say 5%. Then let's say the next one was, let's say 25%, and let's say next one was 50%. Of course, this is maybe my way. And then let's say they go and measure the salt, and they get let's say, okay, let's say you and I think that salt is bad for the soil. Too much salt is bad for the soil. Let's say they get high, let's 8. One of the species they get 10. They plant 7. Another one they get 5. Let's say these are 4 plants they do of the same species in the soil. Let's say here they get 5. They get 4. Let's say they get 6, and they get, like, let's say 3. And let's say in the last one of them grows to 2, 4. Let's say one goes to even 7, and one stays at 1. Suppose something that happens. Right. So this is the data. So this is the data from the experiment, right? So these are like your YIGs. So the idea is that now from this data set, you'll have to, and then what you do is, of course, these are just one realization, right? So you don't know if this is the correct value of height if you put a plant in 5%, or if it's a value with a noise. So, but the idea is that this is what you have, and you want to test is there a difference between this column, and this column. If you look at it intuitively, you see, okay, fine, hey, this seems to be low, but suddenly, of course, one guy pops up to 7. So you don't know if it's like an error or if something happened genuinely. In this case, it seems like everything's kind of close to between 6 and 3, so it's kind of in the middle. In this case, definitely seems high. Of course, you have 1, 5, and you don't know what's going on. So that's where the basis of the model comes in, that you want to understand is there a difference in the mean. So what you do is, so one way to think about this whole problem is that you think of each Yij, right, to be distributed as some mean mu I for each of the I. So think of Yij as this the ith population. So my I and j are switched here in some sense, I think, so be careful about this. So this is my Y, the first column. Yeah, so this could be the one. Yeah, there are Yi is the, so this is my Y11 and this is my Yn1. So that's correct. And then what I do is I think of this as this plus a normal random variable Eij. So Eij is normal with mean 0 and variance sigma squared. That's the model I think about, and IID, the independent, the IID. So across I and j, they're all independent. Okay. So this is my population 1, population 2, population 1, 2, and 3. I think of it like that. And these are my observations. Each of them has how many observations? 1, 2. In this case, everybody has 4 observations. Right? This is my observations n. Right? So I would think of this is Y11, this is Y12, this is Y13, this is Y14, right? And this is Y21, Y22, Y23, and Y24. Right? And this is my Y31, Y32, Y33, and Y34. Right? And then the idea is that I think of them as each of them has a certain mean. This is mu1 has mean mu1, right? This is mean mu2, and this is mean mu3. Right? So then the idea is that the question is that are these means truly different? Is mu1 equal to mu2 equal to mu3 different? That's one thing. Or from this, can I estimate my mu1s, mu2s, and mu3s? So that's the general project. That's the general project. Was this motivation clear? Someone asked me this question in the beginning. Why are we doing all this? Is it broadly clear?
Yes, sir. So I mean, it's definitely much clearer than.
Yeah, I thought you already done a course in statistics and then regression. That's why I thought you might have seen all this before. That's why I didn't sort of go into why these were important. But this is the simplest example you can take. You take 3 factors you have. You want to see if the population is different. Just do this. That's the first thing you do. Right? Of course, there's another thing that I did not say. Which I did not say in this thing, that you can also have an overall effect. In the notes you're seeing, I would have put an extra mu here as well. It's an overall effect also you can have. I did not put that.
So, Shiva, I have a question.
Yeah, go ahead. Yeah.
So in the first, in the lectures, when you formulated the problem the first time, you assumed that the number of samples in each of the populations are different. Is it a different formulation?
No, same problem. Yeah, here all the NIs are the same. That's all. There's no problem.
Okay.
There's really no problem. See, I thought you had done all this before. That's why I phrased it like a theoretical linear models class. I didn't sort of go into where it came from. The questions you get you get data sets to play with and things like that as we go along. But I somehow thought that all this was already done for you, and I had to start from linear models in some sense. I'm sorry about that.
So to be honest, actually, we have done it, but it's just that it all happened in different contexts that. Suddenly, we seem to have started off from a place which we couldn't. I mean, at least I couldn't.
No problem. I have no. I'm probably much worse than you guys. I take 3 times or 4 times to remember something clearly, and then I forget it after some time as well. So it's not like there's nothing to be sort of nothing negative about it. It's just that I felt that I didn't. Maybe I should have done this as a review class as well. I did not do this. I'm sorry about this. That's all I meant to say. But we'll put this up on the recording that we at least future biases will see it before they come to the material. Okay, good. So can I now go to the last part of how to do these sum of squares and things like that? Why are they independent? And so shall I give a sketch? Is that good? Is a good
just
plan?
So if you don't mind, just one question.
Yeah, go ahead.
So when we define this linear model, the error part of it is not something that we can really model, right? I mean, or is that what we attempt? I mean, mu I and mu I can kind of understand because those are parameters we try to estimate.
Right.
So error just comes in as just to account for the differences. Is that?
No, so there's one way to look at it. One way to look at it is that you think of truly this is an error. Okay, that's one way of thinking about it. But that's one way I think. What in this application, for example, you expect plant growth to be a normal distribution. Right? You don't expect all plants to have the same growth all the time. Right? So it's a natural model. Of course, you can argue now, what is sigma squared? Do I know sigma squared? Do I know sigma squared? That's another study altogether. But okay, so there are let's say there are 2 ways to branch off from here. One is okay, fine. I have this parameter I want to estimate, and this is my model, and I work with it. That's the linear model study. One has to step back a little bit and then think of the whole spectrum in one shot and say, these Yij's may truly be normal. And you're estimating the mean and the variance in some sense in this equation. I know that makes sense. I'm not sure. Okay.
Right. So EI epsilon effectively contributes to that variance.
That's right. Exactly. Epsilon is the way normal, right? So like the other thing is that there's a whole different. I don't know if you've done logistic regression before. The whole thing is if these are categorical variables, then you do something else. You don't do like the sort of. You don't do normal. Yeah, you do something else. You don't do this.
Right.
But these are all classical ideas that one should keep in mind before one gets on something else. I mean, I think it's very useful to sort of play with because one. Okay. Anything else? Anybody else? If anybody else is keeping quiet, if you're shy, just send me on chat. Also, I can look at it myself as well. Whatever. Anything's okay. If I'm going too fast, let me know. Also, I'll slow down as well. Okay. So 2 things I've done. I've given you a sort of a 1 semester crash course in 5 minutes on normal and chi-squared and t. Another 1 semester crash course on sort of how to why are we doing all this. Okay, so now let's go to the last part that I want to sort of play with, and then So here I will since you already have the notes and various things, I just do a little bit differently, and I'll come back to, given the motivation, I will just flip the script a little bit so that it shouldn't be jarring, but I think I'll just sort of do a couple of extra things around here and then sort of come back to this. This may take about 20 minutes, so rather than that short 10 minutes so far. Okay, let me start. So now I just want to go towards the discussion of linear models that we are doing so far. So let me just start the discussion. That's there in this week 3 you all encountered. And crucially, how to identify within variation within groups, which are identified as the sum of squares in some sense. That's what we've been doing so far. So I'll just sort of sidetrack a little bit, and then I'll just come to our discussion in a second. So let's just go to a toy question first, and then come to this, or not a real question, not a toy question, but another question. So I had X, let's say, is a vector. It's a d-dimensional vector. Let's say it's normal with some mean mu, or let's say even one dimension. Let's go step. Let's not needly complicate things. Mean mu X and variance sigma squared X. So let's say I have that, or let's say same variance. I don't want to. And I have another random variable Y, which is normal with mean mu Y. And it's the same variance just for the sake of argument, just like the way I phrased the previous YIG. If I have just two people, and I want to test, these come from two populations, let's say X and Y, and I want to test, let's say the test I want to do is, I want to test just like the botanists want to do. I want to test, let's say, two populations. I want to test if the means are the same versus the means are different. This is what I want to test, right? So then what would I do? So the way one would do is that one would go and sample, let me call this population X in some color, let's say some color, let's say purple, and then the other one, let's say in black. So what I would do is I would just go and sample X1, X2, Xn. You would sample IID from X, and then we would go and sample Y1, Y2, Yn. IID from Y. So one intuitive thing to do was that one could, okay, fine, I'm going to just say, okay, I look at X bar and I would subtract it from Y bar, and that would give me one indication of how different they are. But then what I would do is under the null, we know that both of these distributed as, let's say, mu X and mu Y. Right, that would be the thing. And then I would divide by, again, let's say I don't know, I assume I don't know sigma. Let's say I assume no sigma, then I would divide by what's called the pooled sample variance, which I will not get into today, but pooled sample variance. And I would just do let's say I'm a statistician, I have two communities doing different samples. So I get M samples here, then I would just do 1 over N plus 1 over M. And this I know is like T. Tm plus N, sorry, since I have two different guys, I have Tm plus N minus 2, right? And this is the crux of the way I would test for this, and this is under the null. It's under the null. And if the null hypothesis was true, this would be the statistic T. And then what I could do is I could check the value of the statistic and check within T, what's the probabilities that they occur. That's one. Now, in our case, in this linear models case that we've been doing of multiple groups, we have an array. Right? We have an array of so here next case we have an array. We have an array of, let's say, Y11 all the way to, let's say, Ym1. I'll take equal samples that I'm doing. Y12 all the way to, let's say, Ym2. I have so many groups, have n groups, let's say yn, and then all the way to ym. I'm using different notation just sort of to make it a little bit more interesting rather than using the same ideas that I did last time in the notes in the class. I hope that's not too jarring. And again, I want to do again if saying that mu1 is equal to mu2 is equal to mu1. This is what I want to test, right? That's the same idea that I want to do. Very good. So what I do now is that this is where the techniques sort of veer off from the previous case. I have a simple T. I have to do something a little bit more complicated, and so this is where I have the ith groups mean. So this is like so estimate of mu I. So I have, for mu I, the estimate of mu I I'll have is that y bar I is just going to be the sum from, let's say, j equal to 1 to n. Yij divided by n. That's what I have for each I. Then I have the overall mean. I would just call it as y dot dot bar. It's just everybody, right? So I have sum over 1 times m, summation I equal to 1 to n. So m, and then j equal to 1 to n. Yij by, I already have n. So this is what I would have. Right? And so of course, now this is something that we've also seen, the algebraic fact. So algebra manipulation. What one can do is that one can immediately get the fact that these are, if I take the overall summation j equal to 1 to n, this is kind of the algebraic fact sort of is the backbone of this entire analysis, is 1 to m. And if I look at just the mean, each point minus the overall mean, that is y bar dot dot whole squared. If you do the algebra correctly, then this will be equal to two things. One is that, so I think I've called it sum of squares between and sum of squares within. So here I will just put each of these guys, I will just replace them by y dot, y bar I dot, which I have defined above, right? So I define above, I dot. And on this side, I would just get plus. I would have the same thing. Let me go back up here. I will just paste it so that I can go a little quicker. I think here I'll have another n times. Here I can put all the means. That is y bar dot I. So all I did was add and subtract the y bar I. This is an algebraic manipulation of the whole thing. So the sum of squares within and sum of squares between. That's what the two things give you. So this is within a sum of squares and this is between. Right. So again, now the key understanding is that again it's the same idea, right? Here it's x kind of an xi minus x bar the whole square, except the I has an index going from like j equal to 1 for each fixed j. It just looks like xi minus x bar whole square and the sample variance, right? That's why this is an automatic chi-square. And similarly here as well, there's no other difference. Why it's chi-square? It's the same idea, like the first page that I wrote down. That it's the if you assume normal data, if you assume Yij is a normal, so if you assume Yij is a normal, sorry, Yij are all normal with mean y and variance sigma squared, like I've done, right? Then this just looks like the sampling distribution that I discussed in the beginning, right? It's like, so this will be exactly how many of them are there. There are m times n minus 1. So each of them is n minus 1 chi-squared, and I have m of them, I get m times n minus 1. So the first thing you observe is that as done on page 1, right? So you will get that the sum of these guys is again, so I'll write this in different color. Let's say each of these guys is like, let's say in pink. So each of these guys is chi-squared n minus 1. I have m of them, they all add up, and I would just get, and I have to I haven't divided by the variance, so I'll divide by, I had a 1 over sigma squared, and this will just be chi-squared with m times n minus 1. That's what it is. So it's just the same observation as s squared in the first one that you can quote. And this is of course is true regardless of, this is what's important about the statistic is that this is the within sum of squares, right? This is the within sum of squares. This is regardless of the null hypothesis. You don't believe it's mu I, it doesn't matter. This only involves the data, right? So it's like so let me write this down. So this is SSW by sigma squared is exactly this. So the crucial thing is that this doesn't give you anything about, doesn't really care about what the null hypothesis. Okay, this doesn't depend on the null. Does not depend on null. It does depend on the normality, but not on the null. It doesn't care if the mu I is the same or different or anything like that. That's one thing to keep in mind in this calculation. Then the other one, you also know the same thing, this is as done on page 1, the same thing applies to this as well, this statistic as well. Right? You can just check again. So you can just go check again that, let me copy this, same way like I did s squared, it's again, it's like an s squared. So let me copy this down, let me put it here. Let me make this again in pink. It's the same way. If I do this, if I take this, and I divide by sigma squared, right? This is just my sum of squares between by sigma squared, right? Right? And this again, you do a little bit, look at it carefully. It's again, how many does it have? Let me just so let me just do it. Let me just remove the y, this thing right here. Let me just keep it like this. So I think I made a mistake in the algebra here. I'm sorry about that. Here it should be just this algebraic fact I made a mistake. I always make a mistake in this thing when I do the calculation. Let me just go back and check it. This is just n times this guy, right? So there's no j here. I'm sorry. No, j has come out as n. So I'm sorry about that. It's not. So again, it's just m minus 1 chi squared. So you just get again exactly what you had before. You just have chi squared m minus 1. There's no sort of very, very intuitive idea how it is from. And why are they independent? They're independent the same way, right? Independent. For example, here, look at this. Each of these is like yij's, and this is like bars, right? So this is like in quote unquote, in the old example I did, I had xi, the sample mean was independent of s squared. It's the same idea. Like so, the one can actually show the following. It follows from the following fact that if x1, x2, xn are IID, normal random variables, that means same distribution, same mean and same variance, then a fact is the following, that the vector, the minimum x bar is sample mean, and the vector, let's say x1 minus x bar, all the way to xn minus x bar, these two are independent. So this is one fact one can use to show this, that these two are independent. And so what you do is you think of it in the following way. In our case, think of each yi dot bar is, and the vector, let's say y, how do I write that? So I1 minus yi dot bar, comma yi2 minus yi dot bar, all the way to yin minus yi dot bar are independent. Right. Then all you have to observe is that this guy is a function of yi dot bar, right? Whereas this guy is a function of yij. So you're on your way. That's it. Right. So again, this doesn't depend null hypothesis true or not. So just out observe that SSB is a function of yi dot bar, so yi dot bars, and SSW are functions of yij's, like yij minus yi bar, yij minus yi dot bar, and then you're on it. That's it. There's really nothing to be done after this. And again, this doesn't depend on null hypothesis true or not. Again, the same way, it doesn't depend on this. This is that the independent doesn't depend on the fact that doesn't depend on the fact that null hypothesis is true or not. Let me see if I can make it in 2 pages. I can show you in one shot both the things. I'll stop the recording. Let me go back here. Right. So start off with this guy. I'll come down here. Where start off with here. Very cool. Very nice. Of course, now we'll do later in the course how to use this and test things, and you can ratio of 2 chi-squared is f. You can work with f and test things. Yeah, okay. I hope this sort of was broadly up the alley. Do you guys have an idea what's going on?
Shiv, one quick question here.
Yeah. Go ahead. Yeah.
So in this formulation, again, we're assuming that the size of populations are same.
If it's not the same, you just have to adjust the algebra a little bit. That's all. I have not done that. That's all.
But that algebraic equality applies even if the population sizes are different, is it?
That's right. I think no, it's just this idea, right? You take xi minus x bar, I add and subtract this guy, and the cross terms will vanish. That's all that's happening. Nothing else is happening. That's all that's happening in this manipulation. There's nothing else happening. So all I did was what I do. I had this y overall mean I had, right? I just added a y dot bar and I subtracted 1. That's all I did. I subtracted and added. That's all I did. And you expand the squares, and then all you have to do is show those cross terms vanish. That's all you have to show.
Got it. Thank you.
Okay, that's all I had to say. If there are no more questions, I think I've sort of covered all the questions, right? I think anything left to cover? I'm not sure. Okay.
Just one other point that I wanted to clarify was the last bit about the estimability of the parameters, right? When the parameters become estimable.
Let's go there.
Yeah.
The notes. Let's go there. Very good. Let's go there. Very good. Yeah, but can we estimate them, right? That's right. That's quite cool. Yeah, right. Yeah. What's the question here?
Yeah. So towards the end, we're trying to prove. So this is, I think, reasonably okay. This portion of it was, I think, reasonably okay. Towards the end, where we are trying to say that the expectation of L transpose Y is equal to P transpose beta.
That's right. Estimable. Something called estimable, right? That's right. This is estimable.
Yeah. So that wasn't very clear to me. I mean, I think mathematically it was okay, but even at a conceptual level, I was struggling to understand this parametric function. What is P doing there? Or I'm just trying to understand what that is.
Right. So in other words, you typically in many cases you can't estimate the beta parameter per se for, like, suppose P transpose let's say 1 0 0, let's say. That means P transpose beta would be beta 1, right? Is that example? So now, and you want to estimate beta 1, right? So then what you do is you have data y. From data y, you want to estimate beta 1, right? So what you do is you come and say, okay, fine, I would just sum up the first row, first factor, and that sum would give me beta 1. That's what you claim that, right? And that would correspond to one particular L. So in distribution, all this is saying is that if you assume Y to be normal with appropriate mean and appropriate variance, the corresponding, there should be a linear combination of the Y's which give you the estimator as an unbiased one. That's all. Does that make sense? So if you, let's say in one variable, it's easy, right? If it's one dimension, then you know that, and beta was the sample mean, you just say, okay, beta of the true mean is the sample mean is the estimate of the true mean. And this expression is true. E of the sample mean is, for example, in my thing, if you go back up here, we know that E of X bar is indeed mu, right? That's why I wrote down here. Correct?
Yes. Yeah.
So all I'm looking for is if you give me a certain quantity that you're interested in, and when do you say it's estimable? When you can find a different, perhaps I don't want to worry, I don't want to keep the same linear combination like before. I can take any linear combination I want of the statistic, but the statistics mean should give me the true mean. That's all.
Right.
So all I'm trying to see is that then only there's a hope, right? Otherwise, there's no hope of getting P transpose beta. If I can't get in an idealized setting, a particular linear combination of sample to get me P transpose beta, I'll never get anywhere. That's the idea.
Right.
And I told you, and I tell you this, and all you have to do is that it has to be a column space of X, and you're done. Linear algebra.
And here in this step where we go from, if you can scroll down a bit, where you've given the proof.
Yeah.
That step where you go from expectation L transpose Y to L transpose X sub beta, the linearity of expectation. So there, I'm just trying to understand how Y just became X sub beta.
Yeah, because
Y
it's again like I'm just trying to be clever for no reason. See, the idea is that I don't want to spoil my notes. I'll write. Let me know if it's clear. I'll come back and fix it also for you. See, suppose I take L. I know Y is. Okay, let me write down and I sort of make it. I'll make it bigger. I'll erase it after that. Let's see. Let me go back here and come back. See, okay. Let me go back here. See, I know why. I'll write one dimension idea, then immediately clear for you what I'm needlessly doing for you. Suppose I take Y, random variable Y is X beta plus epsilon, right? Where epsilon is an all random variable, let's say, right? So what happens here? All these chokeras are constant, right? And only Y epsilon is a random variable, right? Correct.
Right.
And if I take mean of Y, what do I get? I get mean of this guy, right? This person right here, right?
Right. X of beta plus the expectation of epsilon, which is 0.
Right. So then this is constant, so this comes out, right? So I'm just being needlessly over clever with you guys for no reason. I'm not sure. I just thought it's obvious. This is just this plus E of epsilon, right?
But X beta, I mean, okay. I thought there were parameters that had to be estimated, but then how did they become constants?
They're constants, right? They're not random, right? They're given to you. Right? Beta won't be able to, you won't estimate them, right? Beta won't be able to beta n or things you want to estimate.
And X are constants as it is.
X is a matrix, a given matrix, right? Exactly. You find them, you find the best X later on, right?
Right. Okay, so that's why, expectation of Y just becomes X beta.
That's right. That's the model, right? The whole model. See, the whole thing is that, someone, let me delete this word if I want to send somebody else to this. See, the whole thing is that you have to just step back a little bit and then see the abstractness is in the notation. But otherwise, your assumption is each of the Y's looks like some bunch of constants plus an error, which is the random variable, right? These are all just constants given conditional and these are constants, right?
Right.
So your model is Y equal to, I call it Y equal to X beta plus C, right? Whatever, I must have written down somewhere. Let's see. Hopefully it's not. It'll come next lecture anyway. This is the first one. So yeah, I wrote it here, right? This is the model, right? So X is fixed, right? And beta is what you're interested in, right? And your model is this, right? This is hanging around as sort of as the pulse of the mean, and these are just normal 0, 1 another.
Right. I mean, what threw me off a little bit was also, I mean, in the assignment we had to generate these mu I and mu from a normal distribution. I guess that was just done for us to generate the data.
That's right. That's
but
exactly.
That also looked like a random variable just because we were generating the data ourselves. So that's why it was.
Okay. And I think that was okay. I don't want to say I purposely did it to generate the confusion, but that's an important thing to understand as well, right? So you sort of
right.
I mean, it's not like
Sure.
Yeah.
Thank you.
Yeah. Welcome. I'm sorry it was a little confusing. I didn't mean to make it this confusing. It's just notation. Just stay with it. Just always step back a little bit and just write the equation down. It should become clear after that. It's really the devil is in the needful abstraction of the model. Otherwise, the calculation is simple. That's sort of not. Okay. There's no further questions. I might stop here, or I can. If this was useful, just send us an email, and then we can do it once, maybe not every week, but maybe once every 2 weeks. We could sit down like this and then recap what's happened in the 2 weeks. If you think it's useful, we can do that. I don't mind. If you guys would like that. So, but I think to make it more useful, what I would like is either you send Ishan an email or send on the group on the discussion forum a feedback or specific you don't understand. Then we can do a recap like this once every 2 weeks if you guys like it. I would be happy to do that. The only request is I would like a weekday night time. I don't mind late nights on a weekday, but I would prefer avoiding the weekend because I think all of us are sort of juggling time. So, but I don't mind if that's the only time convenient for you. We can do weekend also.
Siva, one more thing, the question which was raised a lot. They were asking for any reference material which they should follow specifically for this course.
Right. So let's see. There's no real good book that I have in mind, but there are many references. Maybe I can send you a list, Ishan, and you can put it up sometime, maybe next week.
Yeah.
So one is you can look at this. I think see there's an interesting book called Statistical Learning. That's a linear model. There's a good book. It's available online. I'll send Ishan a bunch of references, and then you can put it up on the website.
What might help is if specific weeks have good reference in specific books. I think even one problem I had was, I mean, I tried to refer to different books, but then, I mean, I think there were quite a few books that were already recommended.
Right.
But we couldn't exactly figure out this particular, like, for example, Week-3, how do I get it? So there were certain papers that we had to search and all that. But it'd be good if, I mean, I know it's a bit of work for you, but
no, not work for me, not work. I just want to enhance learning. I just want to make sure that I just want to make sure that I get the correct reference. See, unfortunately, I think ideally if all of us had time, I think what you did this week was the correct thing to do. You look at many sources, see what connected, develop understanding, and moved on. But I also understand that your time also is limited, so I should not sort of throw you on a wild goose chase. I can try. Let me think about it. I'll try. Maybe I might take some time to get up to speed with it. Maybe I'll get to it by not the next week, but the week after that. I'll try and get sort of on top of things. I'll try to give you references where you can look at these things properly.
Yeah, sure. I'll try. Because I think we are also constrained. It's not more. I mean, it's more than we're constrained by these graded assignments, which are weekly, right? So we get just that week to absorb this.
Yeah, I understand. I understand.
And that's where it gets a bit difficult. I mean, even if we had 2 weeks time, maybe we would have. I mean, at least I could have got my hands much more deep into this.
Yeah, I'm sorry. I'll think a little bit. Let me just give me. I may not get on top of it by next week, but the week after that, I'll try and get on top of this thing. I'll try and see if I can get references. I'll try and do that.
Sure. Thank you so much.
Yeah. Okay. Okay. Shall we close, Ishan? Or should we?
Yes, yeah. Thank you very much.
Yeah. Okay. I'll stop. Thank you. Bye-bye. Yeah. Have a nice weekend.